Welcome back. In this particular lecture, we are going to review properties of a pure fluid. Okay, so we'll start with the basic thing, and that is the phases of pure fluid. We all know molecules can exist in different phases, such as solid, okay, where they are located. The molecules are located in some lattice points, and they oscillate around that point, okay, or for that matter you have pretty much disordered structures such as in liquid, okay, but there is a coordination around a single molecule. That means the molecules prefer to stay around a certain molecule, okay. On the other hand, if you impart more heat, they tend to have more kinetic energy, and essentially molecules are far apart, tending to behave like a gas. So, in general, the simple phases are solid, liquid and gases, okay, and mainly this is due to the attraction and repulsion forces among the molecules. For liquid, you certainly need a attractive force, but solid you can have phases just due to repulsive forces, okay. So, this is something which was around 1950s. This particular aspect was cleared in terms of the necessity of repulsive forces for solid phase. Okay, so let me just briefly talk about the phase change processes. So, I will just take an example of a compressed liquid, subcooled liquid to start with. Subcooled liquid or compressed liquid is a substance that it is not about to vaporize. For example, water at 1 atmosphere and 20 degrees Celsius, or in general room conditions. At these particular conditions, so water behave like compressed liquid. Now, in order to vaporize, you need to heat it up. So, if you provide a heat, okay, and this is an example of a piston cylinder, okay. So, we are keeping the piston mass in such a form that the P atmosphere is, that is the 1 atmosphere, is kept constant in the system, and in this case when you heat it up in such a way that the temperature rise to 100 degrees Celsius. At this point, the first few bubble of vapor is formed, or that in other word the liquid starts to vaporize. At this condition, the liquid is saturated, okay, and it continues to vaporize, okay, until it completely vaporizes, that is in state 4. So, intermediate state, that is state 3, where certain part of the liquid gets vaporized. What happens that around or along this path from state 2 to state 4, the pressure, if you see that the pressure and the temperature both remains constant. So, in other word, what is happening that at this point from state 2 to state 3, the temperature is constant, okay, because in other word, for a given pressure the temperature remains constant until all of the liquid gets converted to vapor, okay, and that will be your state 4, okay. So, at intermediate stage you have certain amount of vapor and certain amount of liquid, and for the heating of, we provide more heat. What happens that the temperature starts increasing, because now this is vapor, okay. So, this becomes superheated vapor, okay, upon providing more heat. Now, the superheated vapor by definition is a vapor that is not about to condense, okay, and saturated vapor liquid vapor mixture is the state at which the liquid and vapor coexist in equilibrium, that is from state 2 to state 4. Now, you can present this particular graphical representation in terms of the process on a TV diagram. So, we started from state 1, which is basically compressed liquid for water at 20 degree Celsius, and this is green line or the green curve represent pressure at 1 atmosphere, okay. So, we started from here around 20 degrees Celsius. At this condition, the specific volume is very low, and upon heating we obtain a condition such that at 1 atmosphere we got a boiling point here 100 degrees Celsius, where it starts to boil or start to vaporize, okay, and this it continues okay, and in this point, all these points, these are two phase mixture, okay, vapor and liquid, until the last drop of liquid gets vaporized. So this becomes a saturated vapor. Okay, so this is compressed liquid. This point here is saturated liquid. This point here, the dot point is saturated vapor, and upon further heating it up, we get superheated vapor. So we can continue this exercise for different pressure also. So for different pressure, you will get, of course, curves like this, okay, and so forth. So we can represent this in this plot. Again, is a TV plot of a water at a different pressure, and what we observe is this is the compressed liquid region, and this is your saturated liquid vapor region, this is your superheated region. What you notice is that this point, from the point of a saturated liquid to saturated vapor, the length, okay, starts decreasing as we increase the pressure, and at certain point what we observe is that there is no specific horizontal range or the line here, which essentially means at this point the liquid vapor is difficult to distinguish, and this is the point where the two phase mixture ceases to exist, and this is called critical point. And further increase in the pressure, you do not see any phase change. Okay, so for water, the critical pressure is 22.06, and the critical volume at this is 0.003106 meter cube per kg, and the critical temperature is basically 373.95, and this is nothing but an inflection point. That means the first derivative and second derivative of this curve are going to be 0. Okay, and this can be further explained here in a simpler form. So for any pure fluid, okay, need not be just water, it could be any other fluid, the behavior remains the same. Okay, so you have at a certain temperature less than a Tc, you will observe a range where you will get a phase change from liquid to vapor in this form. All right, and so this is what we call as a liquid, this is what we call this vapor, and above is what we call as superheated gas or vapor. Okay, so this is a typical representation. Okay, at supercritical pressure, there is no distinct phase change, as we already mentioned. Okay, so what we observe here is two things. One is the temperature at which water starts boiling depends on the pressure. Okay, so let me just go back again. The temperature here at which the first liquid starts vaporizing or it boils depends on the pressure. The boiling point, of course, is at 1 atmosphere is 100 degree Celsius. That is what the normal boiling point, but it does depends in general, the boiling point depends on the pressure here. Okay, so that is what we say, that the water starts boiling depends on the pressure. Therefore, if the pressure is fixed, so is the boiling temperature. Okay, for 1 atmosphere, the boiling temperature is 100 degrees Celsius. Now you can find out temperature at which it boils, okay, for different pressure, and that we also call it saturation temperature. In short, we call it Tsat, okay, the saturation temperature, and you can find out also corresponding Psat, and you can plot it. Now what you can notice that once I fix the Tsat, the Psat is fixed. Okay, so Psat is fixed for 100 degrees Celsius. Okay, so in other words, the degree of freedom for defining such a state is just 1. Okay, that is also you can obtain from the Gibbs phase rule. Okay, so Gibbs rules says the following, that C is the number of component minus P the number of phases plus 2 is the degree of freedom. Now C is the number of components pure is 1, and in this case where you have a mixture of vapor and liquid, or in the word vapor liquid phases, there are 2 phases plus 2. So essentially it also tells you the same thing, that degree of freedom you need 1 variables to fix in order to find in order to specify the state. Okay. So the property diagram for the phase change need not be just on a TV diagram, you can use other process diagrams as well, such as PV and PT diagram. Okay. So the representation more or less is same, but it gives a different idea. So I will just describe a bit more later, but this is something extremely useful in order to explain the behavior of the phase change on such diagrams. Okay, so let me further point out here. So let's again take a TV diagram of a pure substance just to summarize. So what we have learned is the following, that if we change the pressure, okay, the boiling temperature changes. So, in other words, you have P1 and this is P2 and P2 is greater than P1. If we can join all these points at which the liquid vaporizes, okay, this curve will become saturated liquid line. Okay. So, this will be from here till the critical point, and the other point where you have a saturated vapor where the first drop of liquid will form if you are reducing the temperature on a constant pressure line, then that will become your saturated vapor line. So, this is after joining this. Okay. So, this is your saturated vapor line, and this region is basically your saturated liquid vapor region. Okay. This is your superheated vapor region, this is your compressed liquid region, okay, and of course, this is your critical point. So, this is a summary of that. Later we will be talking about metastable and other aspects. We will come back to this graph again, okay, but for simplicity we are just mentioning this for the sake of reviewing the earlier understanding of engineering thermodynamics. So, this was a TV diagram. Now, if it is a PV diagram, okay, so the PV diagram here represent here the same regions are same, compressed liquid, superheated vapor, saturated liquid and critical point. However, the isotherms, okay, the slopes are going to be different from the ones which we are using on TV and isobars. So, the slopes are here negative. Okay. So, in other words, you can consider this representation. So, you are maintaining the temperature here, and if you are reducing the pressure, if you are coming from here reducing the pressure, what happens is the volume is going to expand. Okay. So, this is the representation, and thus it will start from here until it reaches the point where it will start vaporizing. So, as we reduce the pressure until it reaches a point where the liquid start vaporizing, it will remain in a compressed liquid region, and then it will reach to saturated liquid vapor region until all the liquid gets vaporized, and subsequently the volume keeps expanding, and thus the slope is negative and it will be in the superheated region. So, the rest of the definition of the region remains the same. So, this is the PV diagram of a pure substance. Now, in general you have three variables, the pressure, volume and temperature, and thus you can obtain the surfaces, thermodynamic surface, okay, and this is a representation of the 3D PVT surfaces. So, which is more complicated in order to understand that, and this is the reason that we often work on a two-dimensional diagram such as PV and TV diagram. Just to take an example of this, this is a PVT surface for substances which expand on freezing. Okay. So, the example are water, and that is due to the hydrogen bonding. Okay. So, this is the pressure, this is the volume, and this is the temperature. You have a liquid solid vapor region. Then you have a triple point line here, okay, and then you have this liquid vapor region, okay, and these are different isotherms which are being drawn like B, H and so forth, and you can take the projection on a PT diagram or PV diagram. Okay. Now, this is little interesting because this region is broader in volume than this region, and that is what the expansions are. So, if you take a PV diagram, it looks like this. This is the pressure and volume again, and as this is a little busy plot. So, again this is a critical point, this is the two-phase region for the solid vapor, and this is a two-phase region for the liquid vapor, and for solid, so this is a liquid and this is basically the region where the solid liquid coexist, and of course, this is your solid region, and some volume of course cannot be accessible. So, this is much easier in this PT diagram, and that's the reason that it usually used in order to explain the phase transition for a pure substance. So, you have this solid and vapor, this is your sublimation line, this is your fusion line, this is your preservation line, okay, and this is your triple point where these three phases coexist. Okay. So, this is your triple point, okay, and this is again solid, liquid and vapor. Now, this curve is basically has a negative slope because of the fact that this is for substances which expand on freezing. Okay. Now, for the case of substances which contract on freezing, this fusion line has a positive slope. Okay. And this is also evident from the PV diagram. If you look at it, these curves are more or less straight, but in the other case it has a little bit curve on the other side. So, let me summarize in this form. So, again this is a PV diagram for substances as contracts on freezing, okay, and this is a PV diagram which expands on freezing, and that is evident from this dashed solid liquid lines. Okay. So, on a PT diagram, this is the melting and fusion curve for substances expand on freezing. This is the melting and fusion curve for substances contracts on freezing, vaporization curve and sublimation. Okay. Now, you can have phase transition along this various different regions. So, let me just take an example of a fusion line. So, you can have phase transition if you are coming from, let us say, E, which is a solid phase, and if you increase the temperature and falling at a constant pressure, the first you are going to get a phase transition from solid to liquid. Subsequently, you will get a phase transition from liquid to vapor. Okay. On the other hand, here from C, okay, you will reach a triple point where all these phases coexist, and subsequently you jump directly to vapor. On the sublimation line, you will directly jump from A, okay, till this coexistence point where these two phases will coexist, such as in this case vapor and solid, and subsequently when the solid will vaporize directly to B. Okay. So, of course, there will be certain heat which will be required in order to change the phase, and this latent heats which is often called for sublimation, okay, for fusion and vaporization will depend on temperature. So, for example, if temperature and pressure, for example, if you are coming from here to here, the value of the latent heat will be different, okay, compared to, for this case, E to F. Okay. The phase transformation will be a little bit different if you are, let us say, coming from point from here, which is a case for substance that expands on freezing, is a liquid phase, and if you are decreasing the pressure at a constant temperature, you will reach solid phase and subsequently reach vapor phase. Okay. On the other hand, for the liquid, in the case of substances for which contracts on freezing, you will get directly liquid to vapor. Okay. So, for this case you have liquid to solid to vapor, whereas in this case it is simply liquid to vapor. Okay. So, the sequence of the phases may vary depending on the type of the phase diagram, which is a PT diagram. Okay. That there could be many solid phases which can exist. An example is basically allotropes of carbon or ice. They have many different phases of that. So, the triple point which we defined is basically for the point where basically the three phases coexist. For a pure substance, of course, the degree of freedom is 0. So, if you use the Gibbs phase rule, it will be just 0. So, there is only one point such that you have these three phases, vapor, liquid and solid, coexist. But in addition, you have many possibilities of other kind of triple point. So, take an example of a carbon. So, you have pressure and temperature plot here, and of course, this is our triple point where vapor, liquid and graphite coexist, the solid phase coexist, but there could be another triple point where two solid phases coexist with liquid. Okay. And that is also known for ice, for example. This is one triple point, this is another triple point and so forth. So, there could be many triple points, but there will be only one triple point where a solid, vapor and liquid coexist. So, there is only one triple point, such triple point. Okay. So, with this I will stop here, okay, and we will continue our understanding of the properties in just like it's like a review of the properties in the next lecture. So, see you in the next lecture.